In maths, our operations have inverses. Addition has subtraction, multiplication has division, and so on and so on. Well, so do our relations as well. So inverse relations. What an inverse relation will then do, it has to undo the relationship. So it'll return our set of dependent values back to the original set of values. Simple example here. Here's a set A going to set B. It uses the relationship y equals x squared. Now if I want to send that back to another set, I could use the relationship y equals plus or minus the square root of x. And in effect, I've got the same set. A and C would actually be equal. They're the same. So I've applied the inverse and I've undone the relationship. How do we find it? Well, a simple way of finding it is simply swapping the x and the y values around and then making y the subject, and you've got it. So y equals x squared was the one that I just did. How did I know it was going to be plus or minus the square root of x? Well, if I swap the x and the y around, I get x equals y squared, make y the subject of that, and there's y equals plus or minus the square root of x. But what about domain and range? Well, because we're simply swapping the x and the y values around, then the domain of the relation must become the range of the inverse relation, and the other way around would be true as well. So x and y's are swapping, domain and range swap over. And if you were to draw both of them on the same number plane, they will be symmetric, but symmetric in the line y equals x. They would be reflections of each other in the line y equals x. If I had this relationship then and I simply had to draw the inverse, well, if I just dot in y equals x, that's going to be my axis of symmetry. Key points then to swap over. Because I know the x and the y's are swapping, the x-intercept must become the y-intercept, and so will the other x-intercepts. The y-intercept must become the x-intercept. And then I can just pick other key points. These turning points, reflect them through the line y equals x, and I'll get the new position. So how do I reflect them? Well, I'm just drawing a line at 90 degrees to that axis of symmetry, and then just measuring the same distance either side. And then I can just pick other points, as many as I like, until I've got a feel for it, and woo, there would be the inverse graph. And if you were to tilt your head 45 degrees, you'll see, oh yeah, look at that. They're a mirror image of each other. Now that brings up the idea of inverse functions then. Remember, not all relations are functions, not all inverse relations are inverse functions. What is an inverse function? If there is a one-to-one relationship, so if that function is one-to-one, then it will have an inverse function. So rather than calling it the inverse relation, we call it the inverse function. How do you test for it? Well, you can do it visually. Remember, to see if it was a function, we did a vertical line test. So because we're swapping the x and y's around, to see if that function has an inverse function, we could look at a horizontal line test. The other way is to look at the actual equation itself. So when x equals function y is rewritten, you get something that's unique. So back to y equals x squared again. There's y equals x squared. It certainly is a function, satisfies that vertical line test no matter where I put it, but it fails the horizontal line test. It is possible to draw a horizontal line that cuts it in two places. So it will not have an inverse function. It'll have an inverse relation, but not an inverse function. Algebraically, there's the x equals y squared again. As soon as I find myself saying y equals plus or minus, well, that's saying it's got two possible values. It's not unique, so it wouldn't be an inverse one. There's, a very dodgy y equals x cubed. But alright, our cubic, yes, it would satisfy the vertical one. It would also satisfy horizontal, no matter where we place it. So yeah, that would have an inverse function. If I was to look at it algebraically, x equals y cubed, well then y is the cube root of x, and if we're just dealing with real numbers, there is only one cube root of x. So it is unique. In fact, what's the difference between these two pictures? The one that has an inverse function, because it's one-to-one, you'll find it's always going to be continually increasing or continually decreasing. As soon as it stops and turns back over, then it's going to fail the horizontal line test. So you're looking for something that's continually increasing or continually decreasing. A couple of years ago, they gave this question. So there's the cubic, and it said, it was a multiple choice question, as you can see. Which of the following functions have an inverse relation whose graph has more than 3 points with an x-coordinate of 1. If we talk about inverse functions, we can make this easier. Because they've said which one has an inverse relation, why couldn't I have reworded this question to simply say, which of these functions has a graph with more than 3 points with a y-coordinate of 1? Just swapping the x and y's around. That's going to be a simpler thing, I think, to work out. So we're simply saying which one of these 4 would have more than 3 points with a y-coordinate of 1. Well, let's look at them. Y equals the square root of function x. What did we say about that? Well, we said whatever was below disappears, and then 1 stays as 1. There's the actual picture, but 1 was the key thing. It's got 3 values, so it's not that one. The reciprocal graph, well, drawing those vertical asymptotes, again 1 stays as 1. And if I was to draw that one in, it's got 3. Function absolute value x. Okay, absolute value x means the y's, we get rid of the negative, we reflect over. It has 3 points. It must be this one. Well, let's confirm it. Y is the absolute value of function x. We said, well, whatever's below gets reflected above. And if I have a look at that, yes, indeed, that has 4 points with a y value of 1. So y equals the absolute value function x was the one that they were looking for. Okay, that shall do us for today.